Hello, dear students. Welcome you all. In this lecture, I'm going to discuss Wien's displacement law. Wien's displacement law. Clear? This law, Wien's displacement law, was actually given by uh, German physicist Wim Wien in 1893. Clear? uh, German physicist Wien in 1893, right? So this is a very important uh, relation of thermodynamics. If I go to the statement of this law, then according to Wien's displacement law, the wavelength lambda m corresponding to the maximum energy, clear, is inversely proportional to the absolute temperature T of the body. Clear? So this Wien's displacement law states that uh, any material that has a temperature T greater than the temperature of 0 Kelvin, clear, that material will emit radiations, and the wavelength corresponding to M stands for maximum energy. Clear? Is inversely proportional to the absolute temperature T of the body. Clear? So this is the relation. If I remove the proportionality sign, lambda m is equal to V upon T. Here B is proportionality constant and it is equal to V is equal to 0.2898 centimeter Kelvin. Clear? So this is the value of this constant. Now, first of all, we will understand what is the importance of this law and how we can drive this law, right? So as far as the derivation of this Wien's displacement law is concerned, we are going to drive it by using the Planck's law, right? Planck's law, clear? We have derived Planck's law by using uh, Bose-Einstein statistics. So we will make the use of Planck's law for driving Wien's displacement law, right? But first of all, we will understand what is the physical significance of this Wien's displacement law. So as I told you that according to this law, every material, every object that has temperature greater than the temperature of 0 Kelvin, that should emit radiations, clear, of certain wavelength. And lambda m is inversely proportional to 2, that is given by this relation, right? So this relation help us to calculate the temperature of different objects in the universe, right? If we know the wavelength of the radiation coming from that object like a star, clear, then I can tell that what is the temperature of that star. So this is very useful, clear, in determining the temperature of the different objects. Additionally, this concept is used in the night imaging, night vision. You might have heard of IR cameras, infrared cameras. Yeah. You might have heard that the viper snakes uh, use IR sensors, infrared sensors. Clear? Now, how they use these IR, sensors? This is very interesting. So, if we look at the temperature of all the mammals that are present on Earth, then most of them has temperature more than 300 Kelvin. Clear? Their body temperature is more than 300 Kelvin. Now, if I put this temperature here, put the value of B, then I found lambda M nearly in the region of far infrared to infrared region. It means all the mammals, clear, they emit radiations of this range, clear, infrared to far infrared region range, clear, in the electromagnetic spectrum. Now, we human beings, our eyes are not sensitive to detect these IR signals, clear. That's why we are not able to see the objects during the night time. But imagine if a, instrument, or if uh, like a snake, like viper snake, if that is able to detect these IR signals, these IR radiations, then that thing, that species or that instrument is capable of identifying the objects during the complete darkness, right? So this is the principle on which IR cameras work, right? IR camera take the image of any object that has a temperature greater than 300 Kelvin. So obviously that object will emit certain radiations in this region. So IR camera is capable of recognizing these IR or far infrared radiations, right? And then that will produce an image of that object, right? So this is very important. These cameras are very important in the night vision, IR cameras. Similarly, as I told you, that there are certain species of reptiles like viper snakes, clear, pit viper, Russell viper. All they have, sensors on their head. Clear? These sensors are capable of detecting IR radiations. So when these snakes search their prey, mouse or some other small creatures, then they use this technique. They look at these creatures and they make the IR image of that creature, right? So that's why they are capable of searching all these small prey in complete dark, because they are using the IR sensors present in their body. Clear? So this is the significance of it. This is very, very important relation that tell us about the temperature of the object, right? Now I will drive this relation by utilizing Planck's law, right? We know very well what is Planck's law. So Planck's law is, in terms of wavelength, we have derived it mu lambda d lambda is equal to minus 8 pi hc upon lambda power 5 into d lambda upon e raised to power hc upon lambda k t minus 1. So this is the Planck's law in terms of wavelength. Clear? In terms of wavelength. Let this is equation number 1. Now I am going to utilize this relation for driving this law. Clear? Now, what is the meaning of this Planck's law? This Planck's law, U lambda d lambda is equal to this. It is actually telling us the energy density of the radiations in the range of lambda to lambda plus d lambda. Clear? Energy density of the radiations means energy per unit volume coming out of that body, right? So I'm going to utilize this. Clear? So as this relation is telling us the energy density of the radiations, then for maximum energy, because we are going to drive this relation that wavelength corresponds to the maximum energy. So for maximum energy, for maxima, I'm going to apply the condition of maximum to equation number 1, du lambda upon d lambda should be equal to 0. Clear? So now I'm going to apply this to equation number 1. It means d upon d lambda bracket minus 8 pi hc upon lambda power 5 into 1 upon e raised to power hc upon lambda kt minus 1. So I put the value of u lambda here, that should be equal to 0. Now here 8 pi hc is constant, so I'm going to take it outside. Minus 8 pi hc d upon d lambda bracket lambda power minus 5 into e raised to power hc upon lambda kt minus 1 power minus 1. This should be equal to 0, right? Now one thing is clear, that this pi's h and c are constants, so though they cannot be equal to 0, so I'm going to eliminate them, right? So now I am left with this term only, right? So when I take the differentiation by using the product rule, then it becomes uh, on the differentiation of first term minus 5 lambda power minus 6 into e raised to power hc upon lambda kt minus 1. Clear? As it is power minus 1 plus lambda power minus 5 into, now the differentiation of this, minus 1 into e raised to power hc upon lambda kt minus 1 power minus 2 into e raised to power hc upon lambda kt into minus hc upon lambda square kt. That should be equal to 0. Clear? This is so. You look at this differentiation. I'm going to explain it. Here there are two terms, two variables. This is variable number 1. This is 1 and this is 2. Clear? So first of all, differentiation of first n x raised to power n minus 1, second as it is. Clear? In the second, we have a first as it is, differentiation of second minus 1 means n x raised to power n minus 1. Okay, then differentiation of this term, that is e raised to power hc upon lambda kt. Then again differentiation of this term, this is this, right? So this is the differentiation. Now I am going to uh, simplify this equation. Then it will become, if I minus 5 upon lambda power 6 into e raised to power hc upon lambda kt minus 1. Clear? Plus, now here it is minus, it is minus, minus minus plus, plus hc into e raised to power hc upon lambda kt. Clear? This term divided by lambda power 7 kvt, kt, not kvt, kt. I'm using only k. In books you can find here kv. Kv stands for Boltzmann constant, so it is understood into e raised to power hc upon lambda kt minus 1 whole term square. That should be equal to 0. Now you look at here, here minus 5, denominator lambda and denominator this hc, where it is hc, clear? Here hc e raised to power hc upon lambda kt, clear? Then lambda power minus 5, lambda power minus 2, where it is lambda, no lambda power 2. So when I took it to the denominator, it becomes lambda power 7. Clear? Then kt multiplied by kt into e raised to power sc upon lambda kt minus 1 minus 2, so denominator 2. So this is the now simplified equation is clear. Now I am further simplifying this equation. So this is negative. So if I take this term toward this side, then it will become equal to here. Clear? Equal to symbol will come here and negative sign will be removed. Clear? So this is equal to this. Right. Now you can see here lambda power 6 and lambda power 7. Clear? So lambda power 7 go. Clear? This is e raised to power hc upon lambda kt. Clear? This is again clear. So you are left with the hc upon lambda kt, clear, into e raised to power hc upon lambda kt minus 1, clear, into e raised to power hc upon lambda kt, clear. That is equal to 5, because on this side we are left with only 5. Now hc upon lambda kt, right, e raised to power hc upon lambda kt and all this, clear. So this is now the simplified equation. This now as we have derived this relation for the maximum energy, so replacing lambda is equal to lambda m. Wavelength corresponds to maximum energy. So here in this equation, hc upon lambda m, hc upon lambda m, hc upon lambda m. All the lambdas are replaced by lambda m. The wavelength corresponds to the maximum energy. Clear? Now I am going to put hc upon k is equal to x and lambda m t is equal to b in this equation. Clear? So what I will get, x upon b hc upon k x and lambda m t is equal to b. So it becomes x upon b into e raised to power x upon b divided by e raised to power x upon b minus 1. That is equal to 5. So when I simplify this equation, it will become x upon b is equal to 5 into e raised to power x upon b minus 1 divided by e raised to power x upon b. So it becomes 5 into 1 minus e raised to power minus x upon b. This is what? This is x upon b. So you can see here the value of x upon b is nearly equal to 5. Clear? Because 5 into 1 minus something. So it is nearly equal to 5. So we can consider it 5, but the exact value is it is 4.9651. Clear? So I am considering this value here. So x upon v is equal to 4.9651. Clear? So from here I got v is equal to x upon 4.9651. Now what was x? X was hc upon k. It was 1. So I'm going to put the value of x, hc upon k into 4.9651. So I'm going to put the value of hc, that is 6.62 into 10 raised to power minus 34 joule second into 3 into 10 raised to power 8 meter per second divided by k. First of all, 4.9651 into 1.38, that is k into 10 raised to power minus 23. So when we will simplify it, all these values, we will get B is equal to centimeter Kelvin. Clear? So we found the value of B is equal to this. So now I'm putting this value B here. Clear? So I got lambda m T is equal to 0.2898, right? Centimeter Kelvin. So it means lambda m inversely proportional to 1 upon T, or I can say it is equal to 0.2898 upon T. Clear? So this is what? This is Wien's displacement law that we have stated in the beginning of this derivation. Clear? So this proves that lambda mt is equal to a constant. Clear? 0.2898 centimeter Kelvin. Right? So it means lambda m is inversely proportional to the temperature. Right? Because it is a constant. So I wrote it in this way. So you can even write it lambda m is equal to B upon T, right? So this is Wien's displacement law, right? So we have derived this Wien's displacement law by using Planck's law. Clear? This was the Planck's law. So we applied the condition of maxima on it, and then we arrived at this result. Clear? So I told you in the beginning what is Wien's displacement law, who have gave this law, what is the importance of this law in thermodynamics. So all the things are explained, right? So thank you very much.